Imagine a world where quantum computing is as powerful as it is interconnected, where instead of a single, massive processor, we have a network of smaller, distributed units working in harmony to solve the most complex problems known to science. This is the vision of researchers like Leo Sunkel, Jonas Stein, Jonas Nusslein, Tobias Rowe, and Claudia Linhoff-Papian from the Institute for Informatics LMU Munich, who are pioneering the field of distributed quantum computing. Their groundbreaking work focuses on finding the best quantum circuit architectures that can efficiently link multiple processors, ensuring they communicate effectively without being overwhelmed by the noise inherent in quantum systems. Scaling quantum power. Distributed quantum computing is about overcoming a significant hurdle in the quantum world: scaling. Currently, quantum computers are limited by their size and the complexity of problems they can solve. By connecting multiple smaller processors, scientists hope to amplify computational power and tackle tasks that are currently insurmountable. But here's where it gets challenging: designing circuits that can handle the intricacies of communication between processors. The team has discovered that standard circuit designs often fall short in a distributed environment. By simulating an 8-qubit circuit across 4 processors, they showed that carefully crafted architectures can minimize the need for interprocessor entanglement, leading to better performance even in noisy conditions. This research is crucial for developing effective quantum algorithms for a future where distributed quantum computing becomes the norm. Distributed VQE, a breakthrough for quantum chemistry. The Variational Quantum Eigensolver, VQE, is a powerful algorithm used in quantum chemistry and materials science to calculate the energy states of molecules, a task that is computationally intensive. Distributed quantum computing offers a promising solution by dividing these calculations across multiple processors, overcoming the limitations of single processor systems. The research involves simulating how quantum circuits can be divided and executed across these interconnected processors. Scientists explore strategies for efficient communication protocols and analyze different network arrangements to optimize performance and minimize errors. The findings suggest that distributed quantum computing can significantly speed up VQE calculations, particularly for complex molecules. However, there are challenges ahead. Future research directions include validating these simulations with experiments on real quantum hardware, exploring scalability to even larger numbers of processors, and developing fault-tolerant quantum networks. Enhancing the efficiency of the hybrid quantum classical optimization process and applying this technology to other quantum algorithms are also key areas of investigation. Simulating distributed quantum computation. In another innovative study, scientists developed a novel method to simulate distributed quantum computation. They engineered a system with 4 quantum processors, each equipped with qubits, to explore how circuits can be divided and executed across multiple machines. Instead of building a physical quantum network, they used a single, larger quantum circuit to simulate this distributed environment. The core of the methodology involved a remote CX protocol to simulate operations between qubits on different processors. The team systematically compared the performance of different circuit architectures under noisy conditions. By first optimizing circuits in a non-distributed fashion and then applying these optimized parameters to the simulated distributed circuit, scientists isolated the impact of distributed computation and noise on circuit performance. They evaluated 4 distinct architectures, including standard and fully entangled circuits, and 2 architectures with alternating local and global layers. This approach allowed them to identify architectures that minimize costly interprocessor communication, delivering improved performance under noisy conditions, achieving 8-qubit simulation in distributed quantum computing. In a remarkable achievement, scientists successfully demonstrated distributed quantum computing by simulating an 8-qubit circuit across 4 quantum processing units. Each unit contained qubits for computation and communication, enabling the execution of circuits beyond the capacity of a single unit. The team used a remote CX protocol to perform non-local operations, effectively connecting the units and allowing for distributed computation. Experiments focused on a binary classification task, rigorously testing circuit performance under both ideal and noisy conditions. The research revealed that standard circuit architectures do not consistently deliver optimal performance in a distributed setting. Instead, circuits designed with minimized remote operations between units exhibited superior noise robustness, yielding better results when subjected to noise. However, the experiments also confirmed that a certain degree of entanglement is necessary to achieve acceptable performance levels, highlighting the strategic importance of connectivity. 4. Impact of entanglement arrangement. This research evaluated the performance of various circuit architectures within a distributed quantum computing framework, utilizing 4 quantum processing units. The team assigned qubits to individual units and implemented 2-qubit operations between them using a remote CX protocol, allowing circuits that exceed the capacity of a single unit to be executed. Experiments involved training circuits for a binary classification task, and then testing their performance under noisy conditions, mirroring realistic quantum hardware limitations. The results demonstrate that the arrangement of entanglement within these circuits significantly impacts performance. Architectures that balance local and remote operations are more suitable for distributed quantum computing. The study provides a simplified framework for evaluating the effects of remote operations and different architectures, offering initial insights into suitable designs for this emerging computing model. However, simulating and training circuits with a larger number of qubits on a network simulator remains computationally challenging, representing a direction for future work. The authors also highlight the need for further investigation into the impact of noise and the development of more robust designs tailored for distributed quantum systems. And this is the part most people miss. While distributed quantum computing offers vast potential, it also raises intriguing questions about scalability, noise management, and circuit design. As researchers push the boundaries of quantum technology, they must confront the challenges of implementing these systems in real-world applications. But here's a thought-provoking question for you. What do you think are the most significant hurdles in scaling quantum computing? And how do you envision distributed quantum computing addressing these challenges? Let us know in the comments.